Hello and welcome to the screencast on finding the inverse of an exponential function modeling temperature change. We're going to look at the example that we saw back in screencast 3.2.6. We had a cup of soup. It had a temperature of 180 degrees Fahrenheit when served to you. After sitting out in a 71 degree Fahrenheit room for 5 minutes, the cup of the soup is 170 degrees Fahrenheit. We found in screencast 326 that f of t equaled 109 e to the negative 0.019 t plus 71 represents the soup's temperature degrees Fahrenheit at time t in minutes, where t equals 0 corresponds to the time the soup is served to you. So actually in screencast 326 we had seen that b, which is equivalent to e to the k, was approximately 0.98 something. So when we solved for k, we were able to get negative 0.019, which is something that you would have done back in section 3.3. So anyhow, we're going to use this model. And first we're going to think about, for this particular model that's given to us, we know the domain is a set of positive real numbers, t greater than 0. And what is the range of this function f of t? So we could think about this two ways. We know in the context of the problem that the initial temperature is 180, and we know that the function f is going to tend towards 71 degrees as time increases without bound. So that basically tells us, since we know the soup's temperature is decreasing, that tells us the range is going to be between 71 and 180 degrees Fahrenheit. The other way we could think about that is to kind of visualize the graph here. We know that the horizontal asymptote is at y equals 71. The y-intercept was at 180, and since we have a negative k value, we knew that we had a decreasing graph. So next we're asked to find a formula for the inverse of the function y equals f of t, and then what is the meaning of this function, what is the domain and range of this function. So to find the inverse of y equals f of t, we're going to have y equals 109 e to the negative 0.019t plus 71, and the inverse is going to be t equals f inverse of y. Remember, the input and output are going to reverse. So that means that we're going to take this equation and solve for t. So we'll subtract 71 from both sides, giving us y minus 71 equals 109e to the negative 0.019t. We'll divide both sides by 109. So y minus 71 divided by 109 equals e to the negative 0.019t. And then to reverse the exponential process, we need to use a natural log. So we're going to end up with the natural log of y minus 71 over 109 equals negative 0.019t. And to isolate t completely, we'll divide by negative 0.019. So t equals, which is also f inverse of y, so I think I'll write it over here, the natural log of the quantity y minus 71 over 109, and all of that divided by negative 0.019t. So that is our inverse function. And then we were asked, what is the meaning of this function? So if t is a function of y now, the meaning is that time in minutes is a function of temperature in degrees Fahrenheit. And so what is the domain and range of this function? Well, we know that the domain and range of an inverse function is this just the reverse of the domain and range from the original function. So for our inverse function, the domain is the y values, which was temperature. And we saw previously that the temperature would be between 71 and 180 degrees Fahrenheit. And then the range of the inverse function is going to be t time. And we saw that time needed to be greater than 0. All right, so let's actually use this inverse function to answer a couple questions. So again, we just have our initial situation. We know that t equals f inverse of y equals this quantity here. And we want to determine the exact time when the soup's temperature is 105 degrees Fahrenheit. So there's two options here. You could take the original function and set it equal to 105 and solve that. But that would actually require you a lot of steps. You'd again have to solve for t, right? Subtract 71, divide by 109, etc. We already did all that when we found the inverse. So really, if we want to find the exact time that the temperature of the soup is 105 degrees, we can just substitute 105 degrees into the inverse function. Remember, the input for the inverse function is now a temperature, and the output is a time. So the natural log of 105 minus 71 over 109, all of that divided by negative 0.019, that indeed is the exact answer for the exact time when the soup's temperature is 105 degrees Fahrenheit. And if you're curious, that's about 61.3 minutes. All right, lastly it says, determine the exact time when the soup's temperature is 65 degrees Fahrenheit. So if you were to try to take the natural log of 65 minus 71 over 109 divided by negative 0.019, you're going to get an error. And that is because, remember, that the domain for f inverse of y, so the input, that was the temperature, was between 71 and 180 degrees Fahrenheit. 65 degrees is not within that interval. So there is no realistic answer. There's just no answer for the exact time when the soup's temperature is 65 degrees Fahrenheit. In context, remember, the room temperature was 71 degrees. So as long as the soup stays in the room, the coldest it's going to get is close to 71 degrees Fahrenheit.